Okay, let's talk about particle physics. Now, particle physics begins with really a discussion of the history of the atom. We start with the ancient Greeks. The ancient Greeks had this idea that if you could take an object and divide it 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 and keep dividing it constantly in half and half and half and half, eventually you would reach something that could not be divided. And that was called atomos. The ancient Greek word for indivisible is atomos, from which we get the idea of the word atom. And their view is that there were basically four atoms: earth, air, fire, and water. Now, this idea lasted for about 2,500 years. And the idea was that there are basic building blocks for matter, for everything around us. And those basic building blocks determine the properties of the big thing. And we still have that idea today. So although the ancient Greeks' idea of what the atoms were is actually rubbish, and we can't really blame them for that because they didn't have particle accelerators in those days. Technology wasn't great in those days. Although they had this crazy idea about what the atoms were, the basic idea that there are basic building blocks and that the properties of the big thing are based on the properties of the small thing, that is still an idea that is going strong today. There are not many ideas that are sort of 2,500 years old and still going strong today, still universally accepted as being correct. Okay, the next idea about the atom actually is about 2,500 years later, and it's the plum pudding model. Now, the plum pudding model has an atom as a kind of a lump of positively charged stuff. In my head, I like to think about this as kind of like a big jelly. And in this positively charged lump, there are isolated negative charges. I like to think about that as being like fruit in the jelly. So an image of an atom in the plum pudding model is a bit like this. And a really important experiment was carried out at this time, and it was called the alpha scattering experiment. And the alpha scattering experiment associated with Rutherford, so Rutherford's alpha scattering experiment, it's also associated with Geiger-Marsden, so it's the Geiger-Marsden alpha scattering experiment. Geiger and Marsden were students of Rutherford. The idea was that they fired alpha particles at a thin film of gold. And the results from that experiment changed the model of the atom. The new model is called the Rutherford model. The Rutherford model has a nucleus that's positively charged at the center where most of the mass is, and a single ring for all of the electrons around the outside. Now, I should point out that at this time, when this model was proposed, Rutherford was not working on electricity. All the people that were doing research on electricity saw this model and suddenly realized that their definition of current, which is the rate of flow of positive charge, was incorrect. In this model, it became obvious that because the single orbitals were touching, it meant that an electron could wander because the orbitals were touching. And actually, in electricity, it's the negative charges that are moving. So maybe current should have been defined as the rate of flow of negative charge. So the reason that we got it wrong, the reason that we got the definition of current wrong, was because at the time when we defined it, the plum pudding model was the model of the atom, and in that model, positives or negatives or both could actually equally move through the material. Now, the Rutherford model only lasted for a few months before the people working on light emission from gases realised, okay, this can't be right. You can't have all of the electrons in a single orbital, because the problem then is that there is no way for those electrons to be excited up to a higher orbital and then lowered back down again and give out light. There's only one orbital. You're either in it or you've escaped out the atom. So within a few months, they realised this model is wrong. And it took about 2 years to come up with the next model of the atom. And the next model of the atom is the one that we sort of know and love, which is the Bohr model, named after Niels Bohr. And the Bohr model has basically got a collection of orbitals, and the electrons sit in the orbitals. And this one explained the absorption of energy as electrons jump up to higher orbitals. That's called excitation. And the reduction in that energy as they fall back down towards the nucleus, which they're attracted to, because they're negative and the nucleus is positive, which is called relaxation. And this explained how light was given off from a gas when you excite it. Now, this idea of the atom started with this concept of something being indivisible. Today, we know that the atoms are not indivisible. The idea here is that this has led to the periodic table of the elements. A list of the basic building blocks that make up all of the matter, i.e. stuff with mass, around us. And that's fine, that works fine, but they're not indivisible. We know that atoms can be broken up into smaller particles, which are the protons, the neutrons, and the electrons, of course. So physicists today use a different term to mean indivisible. We don't use the word indivisible, and we don't use the word atom or atomos. Today, physicists use the term fundamental particle to mean it cannot be divided, i.e. not made of anything else, no internal structure. And there are basically 3 families of fundamental particles: quarks, leptons, and gauge bosons. Now, there are 6 known quarks: up, down, charm, strange, top, and bottom. Or, if you are of a more romantic nature, truth and beauty. And these quarks have fractional charge, and quarks get together to form bigger particles. Now, any particle made of quarks is called a hadron. And there are 2 types of hadron. There's a large hadron and a small hadron. The large hadron is basically a collection of 3 quarks, and they're called baryons. The smaller hadrons are made of a quark and an antiquark, which raises the issue of antimatter. That's with a bar across the top, and they're called mesons. An example of a baryon is a proton, which is an up, up, down, a collection of 2 ups and a down. And if you think about the charge there, you've got 2/3 plus another 2/3, which is 4/3, minus 1/3, which is 3/3, which is plus 1. That's why a proton has a charge of plus 1. A neutron is an up, down, down, which is 2/3 minus 1/3 minus another 1/3, which is why a neutron is neutral. In particle physics, if you ever see a particular link or a particular aspect of the work that is kind of obeyed, I'll give you an example of what I mean by that rather strange sentence in a moment. It's referred to as a symmetry. There is a symmetry between quarks and leptons. And the symmetry is that for every quark that exists, a lepton exists. Now, I don't mean 1 for 1. I don't mean there's a lepton that links itself to the up quark. There's a lepton that links itself to the down quark. What I mean is there are 6 quarks that exist, and there are 6 leptons that exist. So let's look at the leptons. The leptons that exist are the electron, there is one called a muon, and there is one called a tau. And there are three more, and they are all neutrinos. And the neutrinos are associated with these three. So there is an electron, neutrino. There is a muon, neutrino. And there is tau, neutrino. Symbols, charge. These all have a charge of -1 in electronic charge units. These all have a charge of 0. Now, to complete this picture of fundamental particles that are the gauge bosons, the gauge bosons are so-called mediators of the fundamental forces. What a strange phrase. Basically, it's a way of describing how a force comes about. In particle physics, a force is explained as attraction or repulsion by the exchange of particles. There are 4 known fundamental forces: the gravitational force, the electric force or the electromagnetic force, the strong force, and the weak force. And the gravitational force is created by the exchange of what's called gravitons, which we have not yet discovered. The electric force is produced by the exchange of photons, the strong force by the exchange of gluons, and the weak force by the exchange of W plus, W minus, and Z naught. Okay, let's make a comment about antimatter. All particles have an antimatter particle. The antimatter particle has the same mass, opposite charge. If the particle that we're talking about doesn't have charge, like an electron neutrino, then the opposite of 0 counts as 0. So an anti-electron neutrino has 0 charge. But they also have a property that if they meet, if a particle and its antiparticle meet, they annihilate. That doesn't mean if matter meets antimatter, they annihilate. If a proton meets an anti-neutron, that doesn't mean they annihilate, because they're not the anti-particle pair. It's got to be a proton meeting an antiproton. So they annihilate. Annihilate means all the mass turns to electromagnetic energy. And it uses the formula E equals mc squared. Now, one final thing about conservation laws. Now, conserved quantities in physics are really important because they're almost like a gold standard of ideas. If you're not sure what's going to happen in a particular situation and you're not quite sure how to approach that question, then rely on the fact that there are laws of physics and the conservation laws form part of that kind of structure. There are various quantities that are conserved. For example, total energy, charge, linear momentum, angular momentum. But in particular with respect to particle physics and fundamental particles, there are 2 quantities that are also conserved. One is called baryon number and one is called lepton number. Baryon number and lepton number are essentially an indication of whether the particle you're talking about is a baryon or a lepton. So obviously gauge bosons are neither because they're something different. Leptons are not baryons and baryons are not leptons. Baryon number and lepton number only take one of 3 values. The baryon number for a particle is either +1, 0, or -1. And that's the only option. If the baryon number is +1, it means the particle is a baryon. If the baryon number is 0, it means it's not a baryon. If it's -1, it means the particle is an anti-baryon. And it's exactly the same for lepton number. An example of where this particular information is useful is when we're trying to work out nuclear changes. For example, you can see that the top number works. 14 does equal 0 plus 14. That's a consequence of baryon number. The top number is not the mass number. The top number is the baryon number. If it was the mass number and somehow people think that means, well, the mass, then it would suggest that an electron has no mass, which is not true. An electron does have a mass. It's very small, but it does have mass. The reason that it's 0 and not approximately 0 is because it isn't mass. It's the baryon number, and an electron, which is the beta minus particle, is a lepton. It is not a baryon. And if it's not a baryon, it has a lepton number of 0. Now the bottom number is sometimes referred to as the atomic number or the proton number. This is not correct either. The bottom number works 6 equals -1 plus 7 because of conservation of charge. It's the charge number in electronic charge units, and that's why it works. Now if I consider lepton number, you need to remember that we're talking about nuclei here. We're not talking about the atoms. So carbon 14 has 14 baryons. 6 protons, 8 neutrons, each one of them bringing a baryon number of +1. That's why the number's 14. There are no leptons here, so the lepton number there is 0. Now, an electron, a beta minus particle, is a lepton, so it has a number of +1. Don't get confused by the charge. And nitrogen 14 has no leptons, so it's 0. So this doesn't work because 0 does not equal +1 plus 0. So in order to make this work, I have to add a -1. I need another lepton, but it needs to be an anti-lepton because of the minus. And it cannot mess up the baryon number, the top number, and that's fine because it's going to be a lepton. And it must not muck up the charge number. So that only gives me 3 options. The neutrinos. And since it's an electron as part of this process, it will be the electron neutrino that's produced. But it has to be an anti-electron neutrino so that I get a lepton number of -1. Now the same happens for beta plus. And the example here is nitrogen 12 is a beta plus emitter, and it turns into carbon 12, and in order to conserve lepton number, I need to have an electron neutrino. The beta plus is an anti-lepton, which means it has a lepton number of -1, so I need a +1, and I mustn't mess up the charge number. Now the final comment that I will make about this is zooming in here. In annihilation, we see that mass turns into electromagnetic energy. Now I remind you that when we say energy can be associated with motion and we talk about kinetic energy, that doesn't mean that kinetic energy equals the speed, even though that's what we normally think about when we think about motion. Something is moving. What it means is that the link is a formula, half mv squared. Well, mass is an energy. That doesn't mean that mass equals energy. There's a formula, and in this case it's so-called Einstein's equation, E equals mc squared. Mass is a form of energy. It's a form of potential energy. It's certainly not a form of kinetic energy. So if we keep that in mind, that mass is a form of potential energy and the universe is trying to reduce potential energy of all forms, then when we shoot across and look at the 6 quarks that exist, I can basically draw lines between them. They come in pairs. They're pairs determined by the masses. Top and bottom are the heaviest, charm and strange the next, and the smallest mass quarks, the lightest ones if you like, are the up and the down. Now, since the universe is trying to reduce potential energy of all types, and mass is a form of potential energy, then when we look around us at stuff and we look at the particles that are made of quarks, it turns out, not surprisingly, that most of the stuff around us, which is in the form of atoms, is electrons and up and down quarks, protons and neutrons. So the reason that up and down quarks are by far the most common quarks that exist around us is because those quarks have the lowest mass of the paired quarks and therefore have the lowest mass potential energy. And there you go. Particle physics.